Alright, hello everyone. Let's go ahead and find the electric potential due to four charged particles. In the figure below, what is the net electric potential at point P due to the four particles if V equals 0 at infinity, Q equals 5.00 femtocoulombs, and D equals 4.00 centimeters? So first off, let's write what we are given here. So we're told that Q is 5.00 femtocoulombs. A femto is 10 to the minus 15. So this is 5.00 times 10 to the minus 15 coulombs. D is equal to 4.00 centimeters, which is of course 0.04 meters. Now, when we have a discrete amount of particles, and what I mean by discrete, I mean, we can count the particles, there's four. Just a group of particles. We have an equation that we can use to find the potential at some point. Right here in red, the potential is equal to the constant K times the sum from I equals 1 to N of QI over RI. Now this may look a little intimidating at first, but it's really simple. N here is just the number of particles that we have. Here we just have four, and let me go ahead and just label each one arbitrarily. I'll call this one particle 1, particle 2, particle 3, particle 4, whatever. However you want to count them up. So in this case, this would be equal to K times the sum from I equals 1 to 4, because we have four particles, of QI over RI. And if we expand this out, this would be K times Q1 over R1 plus Q2 over R2 plus Q3 over R3 plus Q4 over R4. So just like that, really simple. This is just a compact way of saying all of that. Okay. So let's see what we have here. So V is equal to K. I'm not going to plug anything yet. It's good to plug in your numbers until the very end. So in this case, what is Q1? Q1 is a charge of particle 1. I call this particle 1, and it has a charge of plus Q. So Q over R1. Now R is the separation distance between the particle and the point at which you would like to calculate the electric potential. In this case, this is the point where we want to find the electric potential, point P. The separation distance from point P to particle 1 is D. So in this case, R1 is D. Now we add Q2. Q2, the charge of particle 2, is positive Q. And again, the separation distance from P to particle 2 is D. Now for Q3, the charge on particle 3 is negative Q. So now we have negative Q over D. Again, it's just simply D. And again, similarly, the charge on particle 4 here is also negative Q. So now we have minus Q. However, this time, the separation distance from particle 4 and point P is 2D. So just be very careful of that. It's not D, it's 2D. Okay. So now let's go ahead and, let's simplify this. Before we plug in anything, let's just simplify it. This is equal to k. Okay, well, we have, these two terms will just go to 0. We have q over d minus q over d. And here we have q over d minus q over d. If we were to subtract these two values here, what do you get? You get 2q over 2d. You get q over 2d. Yeah, so if you were to, just do the algebra, you will find that this is all just equal to q over 2d. So now let's go ahead and plug in our numbers here. K is a constant, and it's 8.99 times 10 to the 9 Newton meters squared over Coulomb squared times q over 2d. So q is 5.00 times 10 to the minus 15 coulombs. And we divide this by 2d, so 2 times 0.04 meters. And if you plug that into a calculator, you'll find that the potential is equal to 0.000562 volts, which is equal to, in scientific notation, 5.62 times 10 to the minus 4 volts. And that's it. Not too challenging. Like I said, this part might be a little bit intimidating, but it ends up being very nicely. And yeah, just make sure, it's always good to plug in your numbers at the very end. It's just easier to see each step that you took. I hope this helped you, and thank you for watching.